Hello, class. Welcome to today's lesson. And today we are going to take a look at optimization, which is actually one of the, let's say, one of the things in which calculus is very useful. It's extremely useful. A lot of people, a lot of engineers actually learn calculus in order to optimize functions. So what does that mean first? Let me explain what that means. Optimization. I'm gonna give you two examples. So for example, suppose that you're an engineer working for some company that makes food, and this company packages the food in cans, cylindrical cans. Okay. So suppose that you are given the task of designing a can, and by that I mean finding the radius and its height, which is this. Okay, you have to come up with a design for this can such that it can contain a certain volume. Let's suppose, say, a volume of food equal to 100 milliliters. Let's suppose that. So your boss tells you you have to design a can that will hold this amount of volume inside, and I want you to optimize the design, optimize for amount of material. What does that mean? Well, basically, your boss is telling you get get this task done, design a can that will hold this amount of volume with the least amount of material, which is gonna make the can, right? And it's usually made of aluminum. So all of this side and the lid of the can, you have to use the least amount of material that will contain this amount of volume. And you can do that in basically two approaches. You can either start randomly designing cans. For example, you can make a very large can, very tall can, or another less tall but more wide. And you can do that repeatedly, right? Less tall, wider, less tall, wider, and now this one is very wide but very small in height, and so on. So you could do this in a trial and error approach. All of these cans will contain 100 milliliters of food, but the difference is that all of these cans will have a different amount of material. And I can do the same in both. I can continue doing the same in both extremes. I can continue designing cans which are taller and slimmer, or smaller and fatter, let's say. Okay, so we can adopt that approach, but I mean, you should acknowledge that this is a very dumb approach because you're not supposed to be, like trying stuff, at least not in industry, until you get the perfect design. What you should do is think and reason and do some math in order to get it, in order to get the best design, which let's suppose is this one, in the first try. Okay, you're not supposed to be wasting material in industry. So how can we achieve that? We can achieve that through optimization, and basically through calculus, through the use of the first derivative. And I'm going to show you how in a moment. So this is one example: designing a can that will hold a certain amount of volume with the least amount of material. So basically, in this case, we say that we are optimizing for the amount of material, which is a variable. Let me tell you another example. So as you know, Amazon is one of the biggest companies nowadays, probably the biggest company nowadays. And you should understand what Amazon does. Basically, what Amazon does is this. It's some more complex version of what I'm gonna say, but it's basically the same idea. Basically, the core of the concept is the same. So suppose you have a location like a street, and you want to place a delivery center over this street, either here or here or here. You have a company and you want to build your delivery center along this street. Okay. And you have two customers. You have one customer over here and another customer over here. Customer one, customer two. Customer one, customer two. And I repeat, you want to build a delivery center for your product somewhere along this line. So let's suppose you put it here. And what you're going to be doing every single day is basically this. You pack up some product and then you go deliver it to your first customer. Then you go back, you pack up product again, and then you go deliver it to your second customer. You go back, you charge product onto your truck or whatever, and you go deliver it. You go back, you pick up some product, and then you go deliver it. So you're gonna be doing this every single day, packing and unpacking, packing and delivering product every single day. So it's clear that it's important for you to decide upon which of these points in here along this line is the best decision. For example, you might as well put the center here, and now you're gonna be doing this. You're gonna pick up some product, you're gonna deliver it, you're gonna return to the delivery center, you're gonna pick up some product, and you're gonna do that again for your customers too. Now, in this case, in this scenario, what do you think is gonna be the one of the quantities that as an owner of this company you want to optimize? Because you're gonna be doing this every single day, like going back and forth, or this, or any other place in which you put your delivery center. You're gonna be doing that a lot. So clearly, one of the quantities that you want to optimize is the total distance traveled when you do this. In other words, you want to optimize the addition of distance, this distance, plus this distance. Okay, the sum of both, because you're going to be traveling along this path every single day. So you want to minimize the total distance traveled. Okay, why do you want to do that? Well, that's obvious, right? Because if you minimize the distance traveled, you're gonna save up on fuel for the truck. That's obvious. Okay, you see. And so this kind of thing is what Amazon does a lot. When Amazon tells the trucks, and I suppose you have received something from Amazon. They go to your home and they deliver the goods. Okay, the algorithm, the computational algorithm that Amazon establishes in order to tell the deliverer, like first you have the city, and this is the delivery center. You pack up all the products here, and you have to go today. You have to go to this client which lives here, and then this client, and this and this and this and this, and you have a lot of clients, and you can do the whole travel in a lot of ways. You can go first here, and then here, and then here, and then here, and then here, etc. Or you might have taken another path. For example, you might go from here to here to here to here, here, etc. There is a huge amount of possibilities, and these people actually have software that optimize the best route in order to minimize the total distance traveled and save up on fuel. So this is an extremely important problem. Basically, the problem is this: where should I put my delivery center if I have this client here and this client here, and I must put my delivery center along this street, where should I put it? Should I put it there? Should I put it there? Should I put it here? Etc. So that the amount of distance traveled every single day is a minimum. That's what optimization is, guys. It's trying to make quantity either minimum or maximum because it's convenient, because that's gonna save you money basically, or time or energy or other things. Okay, so that's the gist of the idea. Okay, that's what optimization is. And now let me tell you how we can achieve this. We achieve it through calculus, and more specifically through the use of the first derivative. How does it work? So how do we optimize a function? We optimize it in this way. If you remember, when we have a function f of x, I'm gonna just draw a little bit of the function. For example, right there. This function can continue in both sides, but let's just draw this little part of its graph. So if you remember, guys, when we had this sort of, let's say, apexes or summits, like the top of a mountain, we gave these points a specific name in last semester. We call this turning points. Turning points. Why? Because at this point is exactly when or where the function goes from increasing. Remember that when you move from left to right, if the function is behaving in this way, we say that in this part the function is increasing, and then after the turning point the function is starts to be decreasing. It's less and less and less. So it's going up, 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 turning point, and then the function becomes less and less and less. Okay, now basically the whole idea is this. Instead of calling this point a turning point, which it is, that's a perfectly good, valid name, you must be aware of the fact that this is also a maximum point, a maximum value for the function. That is, for all of these other points in here, in this part or this part, let's select, for example, this point, this point. For this point in particular, this value of x gives me this value of the function, f of x. Let's select another one over here. For this other value of x, which I'm going to call x1 to make differentiate it from this one, the value of the function is this one, f of x1, etc. But for this point, which is the maximum value, for this point in particular, for the turning point, we can see that for that value of x, which I'm going to call x2, this is the greatest or the maximum value of the function achieved, f of x2. You see, f of x2 is greater than f of x1 and f of x for any other point around this neighborhood. You see, this is the maximum value. So the turning point is also a maximum value. And that's the idea. We have to get the maximum. We have to get for what value of x we get the turning point, the maximum value. And if you remember, we can achieve that through the use of the derivative, of the first derivative. Because, let me erase this. If you remember what the derivative tells you, let me also erase this thing. What the first derivative tells you, guys, is the slope of the tangent to a function. You remember that? The slope. For example, if you want to find this, if you draw the tangent to this graph of this function at this point, you're supposed to do this. And if you want to find the slope of this tangent, all you do is the following. You have to differentiate this function. You have to get f prime of x. That's the first thing you have to do. And then evaluate in this particular point, which let me call x1. If you want to find the slope of this tangent, Just evaluate the derivative at this point. In other words, evaluate f prime in x1, and whatever number you have as a result, that's going to be the slope of this tangent, and the same for any other point. So how can I know? How can I know analytically for what x in here, for which of these x's I get the maximum point, the maximum value? Okay, well, what I notice is this. If you remember, at the turning point, what we can observe is that the slope of this at this point, the slope of the tangent, if we draw the tangent, we must acknowledge that the slope of this tangent is zero because it's completely horizontal. You see? So we know that fact. And so basically what we have to do is, one more time, if this is my function f, all I need to do is get the derivative, get it, and then find for what x you have that the derivative is zero, because remember that the derivative gives you the slope, and if I want the value of x for which I get a slope of zero for the tangent, all I need to do is differentiate the function, make it equal to zero, and then solve that equation in order to get the value of x for which this happens. That's how we found the maximum or the minimum points for a function, basically. And that's how we can get the optimization, guys, doing that stuff. So let me tell you an example of how this works. Let me tell you one of the problems that we can solve right away. For example, let's look at this problem. This is a classic problem. So suppose this, you are a farmer, and you want to construct, you have this sort of land. You have some river over here. So this is river, and then you have land in here. You have a ranch or something. And what you want to do, guys, is build a garden, a rectangular garden, which has the river as one of its sides. So for example, you want to do this. You want to enclose a piece of land, of rectangular land here, with wire. So this is wire. You're gonna put wire around this rectangle in such a way. And this side, since you have a river, you don't have to enclose it, because basically, why do you want to enclose a piece of land? Well, because so that animals don't get inside or something like that, right? In order to protect whatever you're gonna grow in here. So you're gonna put wire around this rectangle, and obviously you don't have to put it in here. You don't in this part there's not gonna be any wire. Okay, so you have wire, and let's talk about the restrictions. You only have a limited amount of wire. You have a limited amount of wire. Let's say you have 100 meters of wire total. That's it. And you wanna put it around here. That's it. Okay, fine. Now think about this. What could be a quantity relating to the garden that you may want to optimize? In this case, what would be a quantity that you want to make as large as possible? Because you're going to be constructing this rectangle, and you can do it in different ways. For example, again, this is the river, and for example, you can do it in this way, this kind of garden. One more time, this is the river. You can do it in this way, etc. You see how it means? You can do it in very different. You can change the length of these two sides, and you can choose many combinations. You see, and you're gonna have different possibilities basically. So one of the things that you may wanna maximize in this problem is the area enclosed by the garden. All of this area, the area inside. Why? Because if you have a maximum area, you will be able to grow more stuff in there, whether it's gonna be, I don't know, vegetables, or I don't know, I don't care. So basically, that's one of the things that a farmer could think on maximizing: the area enclosed by this garden. So we want to maximize the area. Okay, fine. So how do we do that? In what way do I need to enclose? In what way do I need to choose this length and this other length, so that the maximum, so that this plus this plus this is 100 meters, and so that the area inside the garden will be a maximum value? Okay, let's see how it works. By the way, this length is also x, clearly, because this is a rectangle. And let's work out the problem. Okay, so remember, we have 100 meters of wire, and we want to maximize the area inside the garden. That's what we want to do. So how does this work? It works in this way. So you're gonna set equations, as many equations as you can, that relate all of your quantities involved. Okay, we can start by doing this. So the area of the garden, that's the quantity that I want to maximize. And so I'm gonna write it down. Area, this is the quantity that I want to maximize. And the area, on what does it depend? Clearly, it depends on the length of this side and the length of this side, on x and y. How? Through a multiplication. The area of this rectangle is equal to x times y. That is very clear. Let's call this equation 1. Now, what other equation can I come up with, can I discover, that relates my quantities involved? What are my quantities? X, y, another time x, and the amount of wire that we have, which remember is 100 meters. Well, the other equation is clearly this one. This side plus this side plus this side should be equal to the amount of wire that I have, which is 100 meters. So 2x, which is this plus this, plus y equals 100. You see, I can come up with this other equation. So now I have two equations to play with. Fine. And remember, what is the quantity that we want to maximize? We want to maximize the area. Now, as it's written right here, the area depends on two quantities, x and y. So we say that the area is a function of two variables, x and y. And so far, we don't know how to do calculus with functions of more than one variable. If you remember, in the past semester, I only gave you functions of just one variable, like so. For example, f of x equals this. This is a function of just one variable. This would be a function of two variables. F of xy equals x squared plus y squared. This is a function of two variables, and we don't know how to handle these ones. We don't do that in first semester. I'm sorry, in high school. And that's the case for the area. We have a function of two variables, and we don't know how to work with this type of functions. So the whole trick on these problems, guys, is trying to get your function, which is the area, as a function of just one variable, So in here, how is this accomplished? It's very simple. All you need to do is this: take the other equation that you have, which in this case is this one, and try to isolate one of the variables, which I'm gonna do right now. I'm gonna isolate the y. So y will be equal to 100 minus 2x, and I can input this value for y, which is all of this, and I can input it in here, right there. So A, the area, will be equal to x times y, but y is equal to all of this. You see? So now I can say that the area is a function of x, and that function is equal to x. Well, let me actually multiply right away. 100 times x minus 2x squared. So this function, guys, now tells me that the area is a function of just one variable, and now we can handle these ones because these are the types that we had been working with before. Okay, so this is the function that I want to maximize. How do I do it? I do this. The first step is get the derivative or differentiate this function. So get a prime of x. Let's do that. Let's differentiate that function. A prime of x will be equal to 100 minus 4x. Okay, that's when you get the derivative of this, you should get this. The second step is this. Make a prime of x equal to 0. So here it goes. A prime of x, which is all of this, I should make it equal to 0. Why? So that I can find the turning points or the maximum and minimum points. So let's do that. How do you solve this equation? Well, you're gonna get that 100 equals 4x, and then finally you will get that x equals 25. After you isolate the x from here, you should get x equals 25. Okay, so this tells me, guys, that at x equals 25, the area gets a turning point. A turning point. Now, how do I know whether it's a maximum point or a minimum point? Okay, how do I know whether, let me actually draw it here. So this is a of x, this is x. Let's suppose that 25 is here. How do I know that at x equals 25, we have a maximum point, or a minimum point? Because both of these are turning points. What I'm sure about right now is that this represents a turning point. It's a point at which the function changes its behavior from increasing to decreasing, or the other way around, from decreasing to increasing. How can I tell which one it is? Is it this one or is it that one? Well, the way to know, as you may remember, is through the use of the evaluation of the first derivative, again, which is this thing. I need to evaluate the derivative a little to the left and to the right from the turning points. For example, let me choose first this one. If I evaluate the derivative a little to the right, I'm sorry, to the left, or a little to the right, let's say 24 and 26, and if I evaluate the derivative right there, I should get the slopes of these tangents. You see? And for example, if I evaluate a little bit to the left of 25, and if I get that the slope is positive, and then if I evaluate to the right of 25, which is, let's suppose it's 26, and I get a negative slope for the tangent, then what that tells me is that 25 is a maximum because the slope goes from positive to negative after this point. It goes positive, 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 and then the slope is 0, and then it will become negative. You see how it works? And then the other way around, if that point 25 was a minimum, what I should observe is the following. This is 25, this is the point. If this point was a minimum, like so, what I should observe is that the slope of these points to the left of 25, let's take this one, should have a negative slope, and the slopes of the tangents at these points should have a positive slope. So when you have a minimum point, the slope of the tangents go from negative and then to 0 at this point, and then positive again. So that's all we have to do, guys. We have to evaluate the derivative a little to the left and a little to the right of your particular point of interest, which is 25, in order to tell whether that point is either a minimum or a maximum. That's what we have to do. So let's evaluate the derivative, which is this, a little bit to the left and to the right of 25. So let's do that. I'm gonna do that in yellow. So let's do that. A prime evaluated in 24, you get 100 minus 4 times 24, and I already did this, and you will get 4, which is positive. And a little to the right of 25, let's suppose it's 26, you're gonna get the following, and you're gonna get minus 4, which is negative. So the slope goes from from positive to negative at this point. Basically, what you're looking at is this. This is 25, and in 24 you have a positive slope, like you see in here, and at 26 you have a negative slope, like you can see in here. You see, so that means that tells you that this is in fact a maximum point, and therefore this is the value at which you have a maximum value for the area at x equals 25, and that solves the problem. Basically, remember, what was the question? The question was, how can I decide upon these values x and y so that my area is a maximum value? Well, we did this process. We found that if x is equal to 25 units, or in this case 25 meters, then the area enclosed by this garden will be a maximum value. Now, of course, you can also, now that you know x equals 25, you can get the value of y, right? Because if this is 25 and if this is 25, then clearly y will be equal to 50. So that this plus this is equal to 100 meters. So y should be equal to 50 meters. So these two quantities, guys, are the ones that you have to take to make your garden so that it has a maximum area. Any other combination of x and y will produce a garden which has less area than this one, than this particular case. For example, if you decide to do this, this is the river, and let's suppose you decide upon this choice. 30 for this side, 30 for this side, and 40 for this side. If you actually build this garden in this way, that fulfills this restriction of 100 meters. 30 plus 40 plus 30, that's 100 meters, but the area enclosed will not be as large as this area. You see how it works? So we say that we have maximized the area of the garden by deciding upon this value for x, 25. It has to be 25. And that's how it works, guys. That's how optimization works. In the next video, I will give you another 2 or 3 examples, and I'm gonna follow the same process. You will see that I follow the same exact process, all of these steps, and by the end of these examples, I hope that you get the whole idea right, so that you can start optimizing functions. Okay, that's it, guys.